Greetings and salutations, Tricks. I'm sure you're sick of my voice, but we're getting there. I reckon about 3 videos to go, maybe 4. And then we're done. Right, we're going to start looking at back to papers 2 stats. We finished paper 1, and we're going to be looking at confidence intervals. You should have printed out these notes over here, otherwise you're wasting your time. Okay, so I know it's the same as the textbooks, but you've got to engage, otherwise it's really not a learning process. So just quickly, I want to have 3 minutes of adrenaline rush and just wing it. So if I have, so what happens in statistics is up to now we've kind of looked at, we've just looked at, we've got our means and our standard deviation from a specific sample. We've got the whole sample in front of us. You've got had the whole class. You worked out the mean. You worked out the standard deviation and all kinds of things from that. Okay, normal distributions, whatever they may be. But now, okay, in reality, if you wanted to measure something, you're not going to be able to get hold of the whole population. Okay, you're going to have to take samples of that population to try estimate what. To try to get a picture of what's going in the real population. And sampling is a whole other field in itself. I mean, to get an accurate sample, what do you have to do? You have to make sure you have, I don't know, the right economic groups, the right demographics, all kinds of things, a sample of all the demographics. And this is why, you know, that whole process of what is the right sample is what makes stats, one of the things that can make stats so misleading. So that is what we're going to look at now. So when you take a sample, or a whole lot of samples. So say you want to estimate, let's say we're going to primarily look at the mean here. Okay, and you want to get an estimate of the mean for a population. Okay, this is all in your notes, you don't have to get it down. Okay, just listen here. So you want to get an estimate of a mean for the population. That population mean, by the way, the symbol is U. Okay, for our population, okay, we want to, and that's what we've been working at now, because we've always worked with the whole population. So now you've got the whole of South Africa and you want to estimate, I don't know, income or something like that. What is that? An estimate of the mean for the income in South Africa. You can't go and speak to every single person in South Africa and find out what the income is. So you take a whole lot of samples. Okay. In a sample, if you take a sample mean, okay, so you can now go pick whatever, 500 people, and you're going to go find out. So you have a sample of 500 people, okay, and you're going to go find, okay, the mean. So you've got all the incomes, you've got all that data. From that data, we get what we call a sample mean. And the symbol for sample mean is that. That's your sample mean. This is your population mean. So this is our sample. From that sample, we want to estimate our population. Now, based on our sample, we can't say that that is the population. You can't say let's say our average income was 10,000 Rand a month. So say you get your monthly income, mean income is 10,000 Rand. Okay, that's your sample mean. You can't say that is, okay, the population that is going to be equal to your population mean. But what we can start saying is we're going to look at confidence intervals. So based on certain parameters, based on this mean, okay, based on this mean over here of your sample, this is your sample mean. So we're going to use your sample, and the size of your sample we're going to call N. Okay, there's your population, there's your sample mean. Okay, we're also going to be given, you're going to be given the population. So from previous studies, for instance, we know that the standard deviation, okay, which the standard deviation stays fixed over time, generally speaking. Okay, the population standard deviation, you're going to be given that. So you say records show that the population standard deviation was whatever. Okay, 800 Rand per month. Okay. So that's going to be, you're always going to be given that population standard deviation of the whole population, not of your survey, of the population on historical records show that the standard deviation is 800. Okay. Now, we can't just say that this means that we can't give a point estimate. We can't say that this means that the population mean is 10,000. What we can start to do is we can start to say, 95, this is a normal distribution, because what will happen is if you take a whole lot of samples, your samples are going to be normally distributed. Okay, your sample, so we're going to look at a normal distribution. All your samples, if you take all your means, okay, of your samples, will approach a normal distribution. So we're going to say 95%, we want to be 95% confidence, okay, that the population mean lies within an upper and a lower boundary. You can choose any confidence interval. You could have a 95% confidence interval. Okay, if you wanted a 99% confidence interval to be more confident that your population mean, okay, we want to know where does the population mean lie based on this. Okay, so we're going to be 99% confidence, we'd have to go out a bit wider. We're going to have a 90% confidence interval. That what we want to see, what we want to be able to say, for instance, is that we want to be, the kind of answer you're going to come up with is that we're 90% confident that the population mean, okay, lies between whatever. So this is 10,000 lies between 9,500 and 10,500. That's the kind of answer we're going to get up with. Okay, we're going to say with 90% confidence that the mean lies within that. Okay, etc., etc. So that's what our objective is going to be. Okay, so you're going to take a sample, you're going to get a sample mean. Okay, you're going to have, and you based on that sample mean, based on the size of your population of the sample, sorry, and based on the standard deviation of the whole population. Okay, we're going to get these what we call a confidence interval. And what does a confidence interval mean? We're 90% confident, okay, or 95 or 99 or whatever it may be, 98% confident that the actual population mean lies within an interval. So we're going to figure out how you calculate those intervals. Okay, hope that made some kind of sense. Probably not. Okay, so if you go through your notes, I'm not going to read it says I'm going to quickly look at some key ideas. Okay, so first of all, they mentioned this whole idea of sampling. Okay, you can't take the entire thing. Okay, and basically this is just a speech about why it's impossible to get all measure the whole population. So if you want to know what's going on in a population, we could get a whole lot of sample means. This x dash means sample means, mu is your population mean. We have to what we're going to try to do is estimate the population mean based on our sample mean. Okay, and they just say that the other estimates we can make. Okay, so and this is what stats is usually about. When we take a sample and use that to make an estimate of what's really going on in the whole population, it's called statistical inference. We're inferring something based on our sample. Okay. Right, and from that you can make something called a point estimate, where you're going to say, we'll explain that now, and you're going to have a point estimate, and you're going to have an interval estimate. So point is, you can fill it in, point estimate and an interval estimate. And a point estimate, okay, is simply any statistic that we can calculate directly from our sample, okay, and it is basically a single number. Okay, so for example, we can say from our population, okay, like a previous one, what I did with the money, you can say our point estimate of the mean is 10,000. Okay, but an interval estimate, which are generally better than point estimates if you're doing sampling, an interval estimate, okay, is an interval we create that will contain the true population parameter with some chosen probability. Let's see something. Makes your life a bit easier. Okay, right. An interval estimate is an interval we can create that will contain the true population parameter within some chosen parameter. Okay, so point estimate not particularly good because it's generally not you can't say with 100% certainty that that's the mean. So just some notation. Population mean, okay, is defined as mu. Okay, the sample mean is defined as x bar. The population variance is defined as sigma squared. The population standard deviation is just sigma. The sample variance, and we're not going to use these at all, is S squared, and that's S. Okay, we're not going to get into this here. The textbook does a couple of examples. I've checked with the examiner. That's not in the syllabus. Okay, then they go on and they do a whole lot of waffle. Okay, we're not going to do the experiment they did. Okay. And you're going to be looking at normal distributions. We look at confidence intervals based on normal distributions. Okay. And you've seen a similar formula here before. Okay. We've used Z is equal to X minus mu over sigma. But now, guys, we're taking sample. The X scores are our mean scores. Okay. X scores are our mean scores. Okay. So we're not working with X, we're working with means. Okay. And we've added another parameter here, and that is this N stands for the size of the sample. So in this formula, which is on your formula sheet, if you look over here, we actually don't use this very much at all, but we use this to get that, which is going to be important. So Z is equal to X minus mu over sigma. Okay, inside you just got to understand these parameters. X bar, as we said before, is a sample mean. From that, we're going to try estimate our population mean. Okay, we're going to be given historical records of the population standard deviation. Okay, N is the sample size. Okay, and Z is your Z scores. Okay, for the confidence interval that we choose. We're going to decide this. We'll get to that all that now. They've mentioned that whole thing. Okay, and this is they just follow mentioning that they follow a normal distribution. So basically, if you took means, so 50 of you went out and did a survey of income, and you took all your means, okay, as your X scores, those means would form a normal distribution. Okay, if we took your means as an X score, those means would form, that's what that diagram is saying to you. You take your means, okay, your means get normally distributed. Just as previously we looked at X scores, and your X scores get normally distributed. If you take 1,000 means, okay, 1,000 people go out and sample 50 people, okay, and you take 1,000 means, those means, okay, will follow a normal distribution curve. Okay, and that's why we're going to use normal distributions. You take 1,000 sample means and you plot them as your X scores, but now we're using X bar scores. Okay, those X bar scores would approach a normal distribution. Okay, and from those X bar scores, we're going to get an estimate, parameter estimates for the actual population mean. Okay, so it says here each tiny box is a sample mean. This is the resulting distribution of the sample means. It appears to be approaching a normal distribution. Okay. Right, let's turn over the page. Okay. So I want to start with this block over here. Okay. And we've got this formula. Z is equal to, okay, from your formula sheet, X minus mu dash sigma over root N. Okay, we know what all the parameters stand for. N is the size of the sample. Sigma is the population standard deviation. Mu is the population mean. X bar is the sample mean. Z is the Z score based on the interval that we want to choose. Do we want to be 95% confidence, 99% confidence, etc.? I'm going to go back to the bit above this just now. So first of all, I just want you to press pause and do a little quick exercise to get your brains going, because I'm sure you're falling asleep, and go isolate mu. Go get mu on its own. The objective of this is we want to get a confidence interval for the population mean. Okay, so go get mu on its own. Okay. Right. So to isolate mu, well, we're going to times Z by sigma root N. So therefore, we're going to get Z sigma, okay, Z times sigma over root N is equal to X bar minus mu. We're looking for mu. So mu is going to be X bar minus Z sigma over root N. Okay. Right. So now, this is our population mean. Okay, we're getting our population mean. Okay, is going to be our sample mean minus, depending on the interval we have, sigma over root N. But the thing is, okay, what we're actually going to do is, depending on where it is, this can become a plus or a minus. Okay, and if you look at your formula sheet, you see that over here. And this is saying to you, your population mean, okay, the boundaries of our population mean, because we're going to be working out not the actual population mean, the upper and lower boundaries, depending on the confidence interval, is equal to your sample mean. Okay, so this formula we don't really use. This one over here we use all the time. Okay, the z-score we choose sigma over root n. So what that means, okay, is your lower boundary, your lower limit or your lower boundary, if I'm working within a certain confidence interval, okay, is going to be equal to your sample mean minus whatever z-score you choose, sigma over root n. That's going to be, so we're going to look at means. This is a distribution of the means. Okay, so your sample, okay, this is a distribution of all your sample means are put together. Okay, the lower limit, this limit over here, is going to be found by going x minus z sigma over root n. Okay, that will be your lower limit. Your upper limit, which is going to be over here, depending on the confidence interval, is going to be your mean plus z sigma over root n. Okay, that's going to be your upper boundary, okay, or your upper limit of your confidence interval. Z is z-scores we're going to choose. Now, what's important, if you look, your error, okay, in other words, the difference between, if I take this formula over here, okay, mu minus x, okay, will be equal to, in other words, the difference between your population mean and your sample mean, which is what we want to keep to a minimum. You're going to be accurate, you want that to be minimized. The difference between, okay, your mu and your population mean and your sample mean. Okay, and that error is going to be equal to plus or minus z sigma over root n. So the difference between what this is saying to you, okay, is the difference between our population mean, the actual population mean, and our sample mean, okay, is plus or minus, plus for the upper boundary, minus for the lower boundary, z sigma over root n. Now z, in other words, you could think of it as absolute values. Absolute value is the distance. The distance between mu and x, okay, is equal to z sigma over root n. And this is telling us something that's quite important. Look, z we choose. Okay, if I want a 95% confidence interval, and we choose it, how big our confidence, how confident we want to be. But sigma, okay, is the population, standard deviation, and root n is our sample size. So this parameter, sigma over root n, okay, determines, those are the fixed things. We can alter z. This determines our level of error. Okay, so and it should make intuitive sense, because the bigger our population standard deviation, the bigger standard deviation is, the more inaccurate things are. There's a bigger spread, we can't be that certain. Okay, and if you think about it, as n becomes bigger, in other words, as your population size becomes bigger, the sample size, sorry, as your sample size becomes bigger, what's going to happen intuitively? The bigger your sample size, okay, the more accurate your estimates are going to be of what's going on in the real population. Okay, as n tends to infinity, okay, that whole thing tends to, okay, so as n gets bigger and bigger, that thing tends to 0. So your error becomes smaller and smaller and smaller. If n was 1 million, something over 1 million is basically 0, which is telling you that your estimate of the difference between your population mean and your sample mean, okay, is going to be essentially 0. So as n tends to infinity, as n doesn't really get to infinity, as n gets bigger, your error gets smaller. Okay, and likewise, as standard deviation of your population gets bigger, your error gets bigger. So those are your two parameters which affect your area, which affect your error between your estimate of the population mean and the actual mean. So it's given a special name, and this term sigma over root n is referred to as the standard error of the mean, which should make some kind of sense. Okay, so I end up over here. in this main block is our formula. Our upper and lower boundaries of our confidence intervals are going to be determined by mu is equal to mean plus minus z sigma over root n. Okay, so we're trying to find confidence intervals. So the lower boundary is x minus z sigma over root n. The upper boundary is x plus z sigma over root n. So what we're going to do is we're going to calculate those values. Let's just say they were equal to, so we put in all our parameters, and this was 9,000 and this was 11,000. And there'll be some kind of symmetry. Remember, your mean of your sample is always going to be in the middle of those. Okay, not your population. We don't know where mu is. Okay, we're making a guess of where mu is. This over here will be x bar in the middle. In other words, the mean of our sample. Okay, so we're going to get, let's say that was, we said, I don't know, 9,000 and 11,000, and let's say this was 95% confidence interval. In other words, this area was 0.95. What we're going to be able to say is with 95% confidence that the population mean is between 9,000 and the upper boundary, which is 11,000. Okay. So the next thing we're going to look at is how do we find, and we've done this before, our Z scores. So this is about finding Z scores for confidence intervals. Finding Z scores for confidence intervals. Okay. So say you said, right, you've done a sample, okay, and we want a 95% confidence interval, okay, for the mean. So remember, this is your sample mean will be in the figure here, in the middle over here. This is yours, okay, and you're going to look for an upper boundary and a lower boundary. Okay, remember what's your upper boundary going to be equal to? It's going to be equal to the sample mean plus z sigma over root n, and this is going to be x mean minus sigma over z sigma over root n. So those are the two values we're looking for. Ultimately, you have to figure that out. To do that, though, okay, I need to first find the z score for that confidence interval. So how do I find a z score for a 95% confidence interval? Well, we're looking for essentially a probability of 0.95, just like with normal distribution. Okay, so if I was going to work with the probability of 0.95 in that region, okay, how did I use my table? Well, I've got to halve this. Okay, so you're going to go 0.95 divided by 2, and we get 0.475. So this area over here is 0.475. Okay, and we want to find the Z scores that go with that. So what do? Well, we go to this table over here, and there is an area of 0.475. The corresponding Z score that goes with it is there and there. So it's 1.96. So for a 95% confidence interval, the Z score here will be 1.96. The Z score here will be minus 1.96. That's why you get this plus minus here, because the plus bit, okay, is for your positive Z score, for your upper boundary. The minus bit is for your negative Z score, for the lower boundary. That's why, even though we manipulated that formula, it looked just like just the minus, okay, but then remember that'll change. The plus or minus bit comes from the fact that Z, okay, for the upper boundary would be positive, Z for the lower boundary will be negative. Okay, so that's how you're going to find the Z score for a specific confidence interval. So if you want to write that in here, we divide the 0.95 divided by 2 is 0.475. Reading off the table, that gives us an area of 0.475 is what we're looking for, which is exactly at Z is equal to 1.96, and using symmetry, Z is equal to negative 1.96. Right, try to get that down. Try to process that. Okay, all this stuff over here. Make some kind of sense to you. That's great. Okay, you'll get, it's actually not bad once you get used to this, guys. Okay. So I'm going to skip out those pages. Okay, just a little reminder. Okay, you can skip out up to 212 for a 95% confidence interval. Your lower boundary would be x minus 1.96. Yep. and that'll be x plus 1,96. We're going to use all different confidence intervals. So let's just practice finding confidence intervals. So say we were looking for, if you go to page 213, okay, a 90% confidence interval. Okay, if you're looking for a 90% confidence interval, okay, what would we go do? Okay, let's just play around a bit over here. Okay, our notes in your notes. So you say, right, that's 90%. Okay, I'd go to 0, that area there is 0,45. That's what we call your H of Z score, is 0,45. Right? Okay, so then you'd go to your formula sheet and look for 0,45. 0,45 is right in the middle of those two over there. Okay, so we're looking at 1,6, and it's in the middle of those two, so it'll be 1,64, 1,645. Okay, and if you look there, there's your Z score, 1,645 minus 1,645. Okay, 95 we discussed. Right, I want you to go try figure out, press pause, and go get the Z scores for a 99% confidence interval. Press pause, try it yourself. Go get a 99% confidence interval. Okay. So if I look at a 99% confidence interval, okay, what are we looking at? Well, this is going to be the area that we want. Here's the middle of your, there's your sample mean, is going to be, okay, remember, and we're trying to find the interval where we're confident. What we're working out is what is the interval for which we're 99% confident that the population mean is between the upper and the lower boundary, based on our sample mean. The sample mean is always in the middle. Right, so what I do here, I take 0.99 is my area divided by 2, and I get 0,495. So this H of Z area is equal to 0,495. Right, that's H of Z, 0,495. Okay, so this is 0,495. Now you go to your formula sheet, and we're going to look for 0,495, which is between here and here, which is 2,5, okay, 2,575. Well, 2,575, that's 8 away. It's a bit closer to that one, that's 6 away. So it's 2,7. If you just use 2,575, that'll be fine. I think they use 2,5756. 2,576. Okay, they use 2,575 would be in the middle. They're just saying it's slightly closer to that. So they do use 2,576, but if you use 2,575, it would be absolutely fine. Okay, so this is 0,495, and that's 2,575 or 2,576. They're not going to penalize you for that. Right. And there's just some other intervals. Okay, so just to be clear, okay, if you look, 90% confidence interval, okay, it's 1,645, 1,655. If you want to be more confident, you got to go. If you want to increase your confidence level, you decrease your accuracy. Because if I increase my confidence level to 95%, okay, 90% I need to go 1,645 across. 95%, I want to be more confident. So your intervals are going to be wider. Okay, the interval where we expect the population mean to be is going to be much bigger. 99%, well, it's even bigger. It's 2,576. So we have, for confidence and accuracy, okay, are inversely proportional to each other. Okay, so the bigger the confidence, the less accurate you're going to be. Okay, so to be more confident, it's made a little note here, you might want to add that. To be more confident that the population mean is in the confidence interval, the population mean mu is in the confidence interval, we need a bigger boundary or a bigger interval. Okay, then we can be more confident, but the price of confidence is accuracy. Okay, right. And then there's just, don't worry about all of this. Okay, right, let's just do one example quickly. Right, it says, okay, so we're on page 214. Okay, if you want to press pause and get a cup of tea, you can. Okay, I can't. So it says, suppose that the something mathematics results, the national mathematics results of learners in the Western Cape are normally distributed with past records showing a standard deviation of 18%. Okay, so first of all, we've got that's past records of the population mean. So that is mu. So mu is 18. I mean, not mu. Sigma is 18. That's your standard deviation. A random sample of 16 learners. So what is the 16 learners? That's your sample size. So that is n. 16 learners in the province had the following marks. So now they actually give you the marks. They don't often do this. First of all, go find the sample mean. Well, we all know to find the mean. We add that up and divide by 16. Okay, I'm not going to waste your time with that. Or you can go use your calculator. You should end up with an answer of 58,5. Okay, so your mean is 58,5, your sample mean. So now I've got my sample mean is 58,5. So I've got all the parameters that I need. Straight away, okay, and based on this, we're going to try to find, okay, based on this sample of 16 people with a mean of 58,5, we're going to try and make an estimate for the whole of the Western Cape maths results. Immediately, that should worry you. Okay, and the thing that should worry you is what? Well, your sample size. Okay, a sample size of 16 is very small. Okay, it's probably not going to be a very accurate reflection, okay, of what's actually going on. Right. So, just a reminder, I'm going to transfer these through. We've got sigma is equal to 18. We've got a sample size of 16. And we've got a mean of 58,5 for our sample. Okay? So those are the parameters we're given in order to try to calculate, estimate population, okay, average, the average of all the maths results in the Western Cape. Right, so we've got that over there. Okay, so the sample mean is 58,5, we can fill that in. The population standard deviation based on historic records is 18, and n is equal to the sample size, which is 16. The first thing we will have to go find is a 90% confidence interval. Okay, so I want to be able to say, right, my sample mean is over here. This is a 90% confidence interval. I can be 90, I want an interval where I can say I'm 90% confident that the mean, okay, of the population for this exam of the whole Western Cape is between such a mark and such a mark. Okay, so if I go get a 90% confidence interval, well, for a 90% confidence interval, what do I do? Let's go through this again. I'm looking for an H of Z score is 0,45. So if I go to 0,45, 0,4, an area of 0,45, it's this pink one over here. Here's an area of 0,45. What did we say that Z score is? It's 1,645, right? So I'm going to be using Z scores of plus and minus 1,645. The plus is for the upper boundary, the minus is for the lower boundary, okay? So the upper limit will be our mean minus 1,645, and this will be the mean plus 1,645, sigma over root n. So go find your lower boundary and your upper boundary, press pause, off you go. So if you go work it out, you're going to get 58,5 minus 1,645. Sigma is 18 over root n is root 16, which is just 4. And you just did to one decimal place, and I get a lower boundary of 51,1%. The upper boundary will be 58,5 plus 1,645, 18 over root 16. And if you work that out, you should get 65,9%. So what can I conclude? I can be 90% confident that your interval is between, that your actual population mean lies between 51,1% and 65,9%. That's the average for the Western Cape's maths results, which tells you sweet diddly squat, quite honestly. I mean, an average of 52 is very different to an average of 64. Why is there problems? Why are these confidence intervals so big? These confidence intervals are so big because n is so small. If you make n bigger, that's going to become far narrower and that's far more accurate. So our problem here is n. Hence, we can be 90% confident that the Western Cape's math average lies somewhere between 51.1% and 65.9%. Right, so that is the 90% confidence interval. What's going to happen to our boundaries as this gets bigger? Well, if I want to be 95% confidence, I'm going to have to go further and further out. Okay, so let's have a look. So next question, we want a 95% confidence interval. Our answer should be smaller than 51.1 on the left and bigger than 65.9 because we want to be more accurate. So 95% confidence interval, what do? Well, you're looking for an area, an H of Z score of 95 divided by 2, and 95 divided by 2 is 0.475, I think it is. Right. So you've got to your table. You look for an area of 0.475. This is the nice one. It's right over there. So it's spot on. It's 1.96, which is why 95% confidence intervals come up such a lot in exams. Okay, so that's going to be your Z score of 1.96. That's be a Z score of minus 1.96. That, by the way, is a Z score of 0. There's your sample mean. Okay, now we need to go find the upper boundary and the lower boundary for a 95% confidence interval. Right, so we're going to use Z is equal to plus or minus 1.96. Press pause. Go find your 95% confidence interval. Off you go. So the lower limit will be mean minus 1.96 sigma over root n. Okay, and so we're going to end up with your mean was 58.5 minus 1.96. Sigma is 18 over root 16. Okay, and we should have with an answer of 49.7%. Okay, and here we're going to get 58.5. On your calculator, you can just enter the 1 and then go back and change the minus to a plus to get the upper boundary. You don't have to show all your working. Plus 1.96. Okay, and 18 over root 16. And so I get an answer of 67.32. So as expected, our boundaries have become bigger because we want to be more confident that the population mean lies within it. So it gets 49.7 and 67.32, which is bigger than that. I've had to spread to be more confident. 90% confidence interval was between 51.1 and 65.9. But if I want to be 95% confidence that my population mean lies in this interval, then I can say only to be 95% confidence, I can say that the mark somewhere lies between 49.7 and 67.32. And again, what's the problem? The problem is n. So we get 95% confidence that Western Cape math average lies between 49.7 and 67.3. Okay. Right, and I want you to go try to do the last one on your own. We're looking for a 99% confidence interval, okay, for the population mean based on the parameters we've been given. Okay, press pause, go try to do it all yourself. Okay, so hopefully you have tried it yourself. So your H of Z score is 99 divided by 2, which is 0.495. Go to your, remember, if I look at Z scores, that's going to be a Z score of 0. Okay, we want to know what our Z score is there, and then we want to know what our upper and lower boundaries are. Okay, so 0.495 lies where? 0.495 we said was in that interval over here. This was a bit of a weird one. So remember, it's fine if you go 2.575, but remember it's actually a little bit closer to this. It's only 6 away from that, so it's going to be 2.576. Okay, is what we tend to use. So Z is equal to plus minus 2.576. If you use 2.575, it's perfectly fine. Right, so you're going to get the lower boundary will be negative 2.576. The upper boundary will be positive 2.576. Okay, and if you go put your values in, you get 58.5 minus 2.576. Sigma is 18 over root 16. Okay, this is going to be 58.5 plus 2.576, 18 over root 16. And the intervals are going to be even wider now because I want to be more confident. So I get 46.9 and I get 70.1%. So the 99% confidence interval is 46.9 and 70.1. Okay, so again, incredibly wide, incredibly inaccurate. I mean, the mean lies between somewhere between 46.9 and 70.1. it's a whole different story. So again, what was the problem? The problem was the sample size of only 16. So you can fill that in yourself. So in the sum, the effect of increasing the sample size, this is what I've been talking about the whole time. The confidence interval calculated will all considerably wide. Why? Because the sample size of 16 is small. Okay. A small value of n makes this term really big. Okay, and remember your error, this determines your error, because if you look at the difference between x and mu, or mu and x, doesn't matter which way, it's equal to z sigma over root n. Okay, that difference. So the bigger n is, the less your difference, the bigger standard deviation, the more your difference. That just, remember, sigma over root n is your standard error of the mean. That determines how inaccurate we are. Okay. However, now, so in the previous example, what we changed was the confidence interval. Now they've done it for you, but we're keeping our confidence interval fixed at 99%. And in the previous one, we worked out that when you had a sample of 16, the 99% confidence interval, okay, we were 99% confident that the multiplied, the average of the population was between 46,9 and 70,092. Let's say I increased that sample size. Now we made n is equal to 100. Okay, they did the working out for you over there. They've just changed n to 100. Okay, I'm always working with z score of 2,576 because I'm fixed on a 99% confidence interval. The only thing that's changing in this formula is the value of n. So when n is equal to 100, then what happens? When I've got 100, when I take a sample of 100, then I can say I'm 99% confident that the mean lies between 53,86 and 63,14, which is already a bit more accurate than 46,9 and 70,092. Okay, so I'm becoming more accurate. It's more meaningful the bigger the sample size. When I say now n is equal to 500, okay, when n is equal to 500, this one over here, okay, what happens? Okay, when I change this to 500, this is your error. Your error becomes smaller because this number is tending towards 0. Okay, and now I can say, based on a sample of 500, with the same parameters, I'm 99% confident. Now I'm getting an accurate picture of what's going on with the population mean. Now I'm 99% confident that the population mean lies between 56,4 and 60,1. Okay, I'm pretty much can see what's going on here. The average must be around about 58, looking at that. Okay, then over here, okay, when n is equal to 2,500, so now I've got a big sample. Okay, I changed my parameter to 2,500. Okay, what happens? Okay, then I become 99. Then I can see the mark 99% confident that the population mean is between 57,6 roughly and 59,4. So I've narrowed it down a lot. Now that's pretty meaningful. So the bigger n, the more meaningful statistical inferences you can make. Just one thing you need to be careful of. The one here they said, what's the area under the curve for all of these? Okay, well the area is 0,99. Okay, it's 99% confidence interval. The area, the shaded region under the curve has stayed fixed. But what happens as n gets bigger? As n gets bigger, your parameters get smaller. Right. Go process that whole thing, guys. Long lesson. Okay, hope it made sense. Okay, couple more to go.